Hello, students, and welcome. Chalo, let's begin. Today we're going to tackle a very important topic from our Unit 10 Wave Optics, and that is Huygens Principle. Now, don't worry about the name. The idea is actually quite simple, I promise, and I'll make sure you understand it in a way that's perfect for your exams and really, sticks with you. Okay, so to get started, let's dive into this with a simple question about something you've probably seen in real life. We'll build a whole concept from there.
Have you ever thought about this? Why don't the waves just stop where the wall is, leaving a sharp shadow in the water? Why do they seem to, curve around and fill up the space behind the wall?
Well, the key to this mystery was given by a scientist named Christian Huygens centuries ago. And his idea, it applies to not just water, but to sound and even light waves, too. It's a truly universal principle. So, what was this powerful idea that explains so much about the world around us? Let's break it down into a very simple model that you can actually picture in your mind.
Now this is the really interesting part. Huygens said we don't need to worry about where the wave started. It doesn't matter if it was a stone dropped in a pond or a distant light bulb. We only need to look at where the wave is right now. Every single point on its leading edge is like a new beginning.
This slide here shows the whole concept perfectly. With a simple analogy, just imagine a ripple spreading out in water. Now picture every single point on that ripple instantly creating its own tiny new ripple. The new, bigger ripple that forms a moment later is simply the line that smoothly connects the outer edges of all those tiny ripples. This connecting line, that's what we call the envelope.
Okay, now this is the formal definition you need for your exams. This is straight from the NCERT textbook. The secondary wavelets, those are the tiny new ripples we just talked about, and the envelope, that's the new wavefront they form by all touching each other. It's really just a geometric way to figure out where the wave is going to be next.
So, the big question is, how does this idea of tiny ripples actually help us predict what light will do, especially when it passes through a narrow opening, a concept we call diffraction? Let's see how this works with a really simple example, the kind that often comes up in exams. We're going to calculate where the first dark spot will appear when light passes through a single tiny slit.
Let's look at the math. It's surprisingly straightforward. This formula right here, A sine theta equals lambda, it's a direct result of Huygens' principle. It basically describes the condition for the first dark spot. Why? Because at this exact angle, the tiny wavelets from the top half of the slit perfectly cancel out the wavelets from the bottom half. It's called destructive interference. So if we just plug in our numbers, we find this first dark spot appears at an angle of about 2.87 degrees. Simple, right?
Now, this is where it gets a little strange. This leads to a key, counterintuitive point you absolutely must remember for your exams. Look at that formula again. Sine theta equals lambda over A. If the slit width, A, gets smaller, then the value of sine theta gets bigger, which means the angle theta also gets bigger. So a smaller hole makes the light spread out more? I know, it's the total opposite of what you might think.
Okay, let's clear up a common doubt now, one that often confuses students and can cost you marks in exams. This is a very common trap, so pay close attention.
This is actually a very logical question to ask. If every point on a wavefront is sending out wavelets in all directions, like a tiny sphere, shouldn't there be a backward-moving wave too? So here's the answer. While Huygens' original idea didn't fully explain this, we now understand that the wavelets going backward interfere with each other in such a way that they just cancel out completely. It's only in the forward direction that they all add up nicely to form the new wavefront. You can think of it like a team of rowers in a boat. If they all push in the same direction, the boat moves forward. Simple.
So the crucial point for your exams is to always think about that envelope, that common tangent line. This common tangent only exists moving forward from the wave. There is no backward envelope, and so there is no backward wave. That's it.
Chalo, let's quickly summarize what we've learned and see where this topic leads us next in physics. This is the part you should definitely note down for a quick revision before your exam.
These are the most important points to remember. See, it's not just a rule for light. It's a fundamental rule for how all waves propagate. And most importantly, it's the tool we use to understand all the other big topics in this unit.
Understanding this principle is absolutely essential, Beta. Why? Because it allows us to derive the laws of reflection and refraction, like Snell's law, right from the basic nature of waves, instead of just memorizing them as some random rules.
Think about that. That everyday observation, that's a direct result of refraction. We are going to use Huygens' principle to answer this very question and derive Snell's law in our next explainer. See you then.